Alright, this is my third attempt to record this. The first attempt, the game crashed. The second attempt, the music and volume of the game itself was so loud that you couldn't even really hear me talk. So this attempt, I'm going to actually, hopefully, get this to be so that you can hear it. We are headed off to Minmus. We're not getting there this episode, but we're going to get a little bit closer. I've learned how to find the ascending node, and I have added a search for the plane change burn vector at the ascending node so that we match and our relative inclination is relatively close. Let's let this guy fly ahead on its own and search for the or look at the search code. Let me close that guy. Alright, so the launch profile is pretty much the same. I've got this Notepad++ extension that I've linked to on my GitHub, and I'll also link to this YouTube episode. The biggest difference is we're now calling this plane matching function, and after we match the plane, then we circularize again, and you'll see why we need to do that in a little bit. And then after that, we release the throttle. We're gonna, after this episode, have to learn how to get a closest approach. So let's look at this transfer script. So the plane matching function will run this ascending node function that I found on the KOS subreddit. It had a bug or two in it, so I've got a little bit in there. It's still got a bug I'm trying to figure out, but we'll talk about that in a second. After we find the ascending node, then we can match the inclination by adding a normal vector burn and then executing that node. So here's the function that I found on the KOS subreddit. It basically looks around using vectors to figure out the angle to the target, and the change that I made was adding this if statement. If while we're walking around the circle, we find that the angle that we're getting is starting to increase, then we can jump forward half an orbital period and start the search over again. Because if we start the search while we're while the descending node is in front of us, then we will not. This function does not work very well. So we need to start the search in front of the descending node and behind. Like the ascending node needs to be in front of us, but the descending node needs to be behind us. So I just basically set the things, the increment, and the last angle to the same thing that it started with, but I set the start time to where the last search was plus half an orbital period. I also changed the angle that we find acceptable to be 0.1 rather than 0.05 because there were cases where it was just not finding the right spot, and that seemed to help. The match inclination function that I have should look very similar to the match eccentricity function. I'd like to refactor this code so that they don't have so much duplication. But in the meantime, I was writing this and I didn't want to screw up the existing code. So it's nice to add code in one change and then refactor in a second change rather than do both at the same time. So I have this target inclination search that we go by tens or hundreds, tens, ones, and then 0.1s, just adding to the normal vector that we're going to burn on until we find a acceptable inclination that's within 0.02 of what we want. The target inclination is Minmus's inclination, which is 6 degrees. And after we've found a closest approach or a closest degree at each of these, we are going to compare if we go forward or backward by tens, which one was closer, use that one. Then so it's very similar to the reduce inclination function. The biggest difference that we have to supply this extra parameter, target inclination, because in the eccentricity one, we're basically saying target 0. So there's an implied thing here. Our epsilon is 0.02. So each loop, now we're checking to see if the last time we looked, the delta is less than epsilon. The delta is the absolute value of the target minus the current node. In this case, we haven't started, so I've got the start inclination is whatever the current node is. We're going to be bumping the normal instead of the prograde this time. On each loop, we update the this check delta, and when we compare to see if we have an X patch, or if this delta is larger than the last time we checked, then we should exit because we've overshot. We return the normal back to the previous loop and set the node to the previous loop, and then we return that. If we've found an acceptable node, then we return, and that's it. The get smaller inclination is looking for the smaller delta of the two. So we compare A and B, we have a target inclination, and we see which one is closer to that inclination. Let's see how we're doing. Awesome. So we've already gotten up to near our Apple apps. We're just waiting to do our burn, and then we'll see the new code starting to run. Let's just go ahead and switch to this view so you can see what happens. I could not have timed that better. Alright, so now we're circularizing 74.9 and 74. Ooh, something happened at the end of that burn. Well, we'll just have to deal with that. So we've calculated a new maneuver node at 240 meters per second, and I'll pop out the oh, I didn't have it all the way out this time so that you can see more of the results, but you can see that the resulting white not white, the dotted orange plane will match the green target plane of Minmus when we run our burn vector. And after we run this, I will also run the circularization function again so that our Apo and Peri are roughly the same. Hopefully it actually does a good job of executing the maneuver. And then we can, in the next episode, here we go. I've got this extra solar system that would take a million bazillion years to fly to. It looks cool, but I don't know if I'll ever go there. Alright, here's our circularization burn coming up. (101) and 101. So in the next episode, we can bring so we can like set the maneuver node like 10 minutes ahead or 100 seconds ahead. Doesn't really matter terribly. Bring the Apo apps of the maneuver node out to the same altitude as Minmus, 46.4 million meters, and then basically walk the time of the maneuver node around until we have a closest approach that's nice and happy. When the closest approach starts getting smaller, instead of or bigger instead of smaller, then we know we've overshot, and we can stop and go back one tick, and then do the move around by 100 seconds, move around by 10 seconds, move around by negative 10 seconds, 1 second, negative 1, until we find a closest approach. Once we've found the closest approach, then we can adjust it until we have a in the next patch the altitude of the flyby periapse whatever we want. So that's what I'm going to be working on. Until then, I now have a relative inclination of 0.01 degrees and a circular orbit to work with. Thanks for watching, and see you next time.